All right, welcome. Thanks everyone for attending. As some of you have probably realized at this point, I just really love learning new programming languages, and especially if they have some unique characteristics, and certainly OCaml has that. At the bottom of this slide, you'll see a URL where you can find all of my slides, and so you'll find these there. Just look for OCaml. And I'll skip this about me. I wrote a book. I'm writing another book on HTMX. That'll be coming out soon. All right, so a long time ago, we had this language called ML, stands for meta language, and it's a functional programming language. It uses the Hindley-Milner type system, and we'll be talking about that again shortly. But ML influenced a lot of other programming languages. And one of those is F#, which is heavily influenced by OCaml, and that runs on the .NET platform. And an interesting way to look at some of these languages is that F# is to C# as Clojure and Scala are to Java. They are ML-inspired languages that run on top of a language that is not ML-inspired. One language that came from ML is Caml. It's short for Categorical Abstract Machine Language, and that's been around since 1985, and that was the predecessor to OCaml. And then OCaml came out in '96, which by coincidence is the same year that Java came out. So the name is short for Objective Caml. It adds object-oriented features on top of Caml, although those don't happen to be used very often with OCaml. And then it adds a more expressive type system. It comes with 3 ways to run your code. There's an interpreter, there's a compiler that compiles to bytecode so that you can run that on any platform, and then there's a compiler that compiles to native executables for a specific platform. There are also ways that you can compile OCaml code to assembly language or C or JavaScript or WebAssembly. All the files you create in OCaml should have a .ml file extension, which is short for meta language. And the performance of OCaml is about 50% of C in most cases. There are a lot of notable features, and I don't want to just read this slide to you, but I'll point out a couple of things that are key. And one is that it has really great type inference, and I'll talk about that more in just a bit. It has a lot of standard things like garbage collection that you're used to having. It also has features that people have talked about adding to JavaScript for many years, and I hope that they do at some point. And one of those is operators for function application, and we'll see some examples of that coming up. And then stronger pattern matching, which you can think of in the case of JavaScript as being like a combination of destructuring and a switch statement. So more on that coming up. Variant types is a very important feature. It's like enums that can have data associated with the different cases of the enum. So many more things. Very terse syntax for defining and calling functions. Limited mutability. So other functional languages like Haskell in particular try to be very pure and prevent mutation. But OCaml, they recognize that there are cases where it really would be good to have some mutation, and so they allow that in some kind of limited ways. Has pretty good performance compared to non-systems programming languages, and I can call out to C if I need to, and lots of great tooling. The OPAM package manager, the Dune build tool, and then UTOP is a great REPL for experimenting with features of OCaml. So let's talk a bit more about type inference. So this is, again, based on the Hindley-Milner type system that many functional programming languages use, and this makes it so good, the type inference, that in most cases, you don't need to specify the types, yet the compiler knows all the types and enforces those. So you can specify types if you want, but that is mainly just for documentation. And one reason you don't need it, even for documentation, is that the language server processor in your editor is so good that you can just hover over a name of an OCaml function and it'll say, this is a function that takes parameters of these types and it has this return type. So how do they achieve this, being able to determine the types without you telling it? Well, one reason is that the operators in OCaml work on specific kinds of values. So in some languages, the plus operator is used to add integers, add floating point numbers, and even concatenate strings. But that is not the case in OCaml. In OCaml, the plus operator is only used to add integers. And if you want to add floating point numbers, the operator is plus period. And if you want to concatenate strings, it's a caret. And so here we see three function definitions. I mentioned how the syntax is so terse. So this first one is saying, I want a function that adds integers. Its name is addInts. It takes two arguments, A and B, and the implementation is just to add those. And I know that A and B are integers because the plus operator can only be used to add integers. Likewise, on the next one, the plus period operator, that's what you use for adding floats. And concatenating strings, you use the caret operator. And so that's how the compiler is able to tell, just looking at that little bit of code, what all the types are. There are many companies that use OCaml, and so I have a list of some of their uses here, and you can check back at this later if you're interested. I won't read through all this, but the ones with the yellow stars are some significant ones. And in particular, I want to point out Jane Street and Teradez. Those two companies not only use OCaml, but they're very invested in the ecosystem and develop lots of libraries for it, and they're involved in moving OCaml itself forward. And there are also languages that derive from OCaml, and all the ones that you see listed on this slide have something in common, is that all compile to JavaScript code. So there's lots of ways that you could use OCaml for web development if you choose to. So if you want to get started with OCaml, there's a bash command that you can run to install it. If you're on Windows, there's an alternate way to do this. And then once you have OPAM installed, that's the package manager, then you run OPAM init. That runs for quite a while and sets everything up. And then you're ready to install some tools. So you're going to want the language server processor right here that works with your editor to give type awareness in your editor. Then there's the ODoc tool that can get comments out of your code and turn that into HTML documentation. There's OCaml format for formatting your code. And finally, UTOP is that REPL tool. So to start up UTOP, which stands for Universal Top Level, you just enter UTOP and you get something like you see in the screenshot there, and then you just start entering expressions. Now, one thing that's a little odd at first when you're using this is that your expressions won't be evaluated unless you end them with a double semicolon. Why two semicolons? Well, the reason is that in OCaml, an expression can be a sequence of expressions that are separated by a single semicolon. And you can put these on multiple lines. So they didn't want to make it so just hitting the enter key caused it to evaluate, because maybe you just want to go down to the next line and enter another line. And so they settled on two semicolons to mean that you want to execute it. You might put some of your source code, maybe defining some functions in a separate source file, and you can load that in with use and give it a path to the file. And then if you have installed a library using the OPAM package manager, you can pull that into UTOP with #require. And then when you want to get out, you hit Control-D, or you can type #quit. You can, there's really good support for OCaml in VS Code. And if you want to do that, you want to install the OCaml platform extension. And then in your projects, in order for code formatting to work, you need to create a file called .ocaml format, and you need at least these first two lines. And then after this, you see an example of how you can override some of the settings if you want the formatting to be a bit different than the defaults. There's no syntax in OCaml for a single line comment, but there is for multi-line comments. And maybe some of you remember back when XML was popular, there was a thing called xquery, and it used a kind of syntax that you see there, parens and asterisks. And so the same thing is used in OCaml. And you can nest those kinds of comments. There's the primitive types supported that you might expect. The only one up here that maybe you're not familiar with is unit, which is represented by two parens. And it's a way of saying this doesn't have a value, or this is a function that doesn't return anything, like void and some other languages. So when you're getting started with this, I think it's useful just to put some sample code in a source file and you just want to run it. And you could use UTOP for that, but another way is to just use the OCaml interpreter. And so you can just type OCaml followed by a file name. And so suppose I created a file that had this content in it, a little hello world example. Then I can just run that with OCaml hello.ml. But once I get to the point that I'm installing libraries that I want to use, or I have multiple source files that make up my project, then I really want to start using the Dune build tool. And some slides near the end that I almost certainly won't get to give you the steps for getting that set up and tell you about how to use it. So check that out. But I do want to talk a bit about what's going on in this line of code. What is this let parens equal? Remember, the parens is the unit value. And what this is saying is that I don't want this to compile unless the expression to the right of the equal has a result that is that unit value. This is a bit like writing a main function in some other programming languages, but it's just doing some extra checking. So for example, if I would have put code on the right-hand side that said 2 plus 3, this wouldn't compile because the result of the right side is an int. That's not the unit value. And so it's making me be explicit and say, I'm telling you to do a thing, and the reason I want to do it is for its side effects. I'm not trying to compute a value. And so it's just an extra check on that. There are a lot of operators supported in OCaml, the ones that you might expect. We don't need to talk through all of these. I just want to point out a couple of things here. One that I mentioned earlier is that there's a separate set of operators for operating on integer values, and then a different one for operating on floating point values that all have a period after them. So that's an interesting feature. And then over on the right here, some other operators. We have some operators that are related to working with refs. Well, refs are one way that you can have some mutable data. And it's like you've put this mutable value inside a box, and you need a way to get it out of the box or to change what's in the box. And that's what those operators are for. And then I mentioned function application. It's a different way that I could have a sequence of functions, and I want to pass a value into the first one, evaluate it, take that result, go into the next one, and so on. And those operators do something like that. So I mentioned that one of the things I really like about OCaml is the terse syntax for working with functions. And this is absolutely my favorite way of working with functions. A, B, C, what does that mean? Well, it means that A is a function, and I'm passing B and C to it. I've always felt like a space is a perfectly good delimiter, and that's what we're using here. Likewise, if I want to define a function, I say let function A that takes parameters B and C be defined by the expression that is on the right of that. I do have to define functions before I call them, and I also get automatic currying, and that means that if I call a function with fewer arguments than it has parameters, I'm going to get back a new function that expects the rest of the parameters, and that turns out to be really useful. So here we have an example where the first thing I do is use the open statement. Printf is a module, and so if I open it, it means I want to take all the values it defines and make them evaluable inside me so that I don't have to prefix them with printf period. And so the one thing I'm after here is the printf function, which is part of that module. Then I want to define a function that adds 2 integers, and so I have that right here. Then add 5, notice I'm calling add with only 1 argument, and so that returns to me a new function that only expects 1 argument, and it will just add 5 to it. Then I have let, which as I said is kind of like a main function, and then I say I want to printf here, and I'm going to do this addition. Notice the parentheses there. So I don't need parentheses to call a function, but if I want to call a function and use its value as an argument to another function, like printf, well, then I have to put the parentheses around it so that it evaluates that first and then passes the result to printf. Here's my comment syntax. Notice I've got a semicolon there. This one doesn't need it. And so this is a sequence of expressions, and the result will be the result of the final one, but the result of printf is the unit value, and so it matches that, and so this works. Okay, now what is the type of the add function? Well, OCaml will tell you that its type is int, arrow, int, arrow, int. What does that mean? Well, it means that really you could think of add as a function that only takes 1 integer. And what does it return? Well, it returns a function that takes an integer and returns an integer. And so if you have 5 parameters, you're going to see a whole bunch of arrows in the return type, and you can call it with as many as you want, and you'll get back a new function that expects the rest of them. Now, what happens if you want to write a function that doesn't need any arguments? Well, now we have a little bit of a problem with the syntax, because if I just said let hello equals some expression, it's going to evaluate that right away, and it's going to think hello is a variable. But if I want it to be a function, I have to signal that somehow. And so that unit value is a way of telling it, hey, this is a function that doesn't really take anything, and there's its definition. And then when I call it, I have to do the same thing again, because if I just said hello, I would be saying, can you give me a reference to the function? It doesn't mean call it. And so if I give it the unit value, it knows that I really want to call it. Yes.
There's a space between function name and the parentheses have to be there?
I think it does, but I'm not positive about that. Yeah. Yeah, so the question is, do you have to have a space before this unit value, or can you put that right up against it? I think you need to have a space, but I haven't actually tried that. You can have named arguments. And so here I have this greet function, and I can pass it arguments that have names. The name of the first one is name, and the name of the second one is suffix. So there's a distinction between an argument label and a parameter name, and they can be the same, but they don't have to be. And so in this case, here, the argument label and the parameter name are both name, but here the argument label is suffix, so I have to use that when I call it, but inside the function, I'm going to refer to it with this shorter name of s. So what this is saying is that you don't have to pass me the name, it's optional, and if you don't, I'm going to use the value world. The suffix is also optional. If you don't pass it, I'm going to use an exclamation point. And so down here, when I call greet and I don't pass it anything, I get hello world exclamation point. But in this call, I give it mark and I give it a suffix of period, and so I'm supplying both, and I get that. Or here, I just gave it the name and not the suffix, and so I get the default of the exclamation point. So notice that when I pass named parameters, I have to put a tilde in front of the name. That's signaling that this is a named parameter instead of a positional parameter. Okay. Function application. This is, I think, a cool part of OCaml and something that I hope comes to JavaScript at some point. There are two operators for this, and they work in a different direction. So there's a double @ sign and then the kind of right pointing triangle. So here I define this function double, pass it in a number and multiply it by 2. And what is the type of x? Well, it has to be an int because I use this operator and that only operates on ints. Then I have square that multiplies an int by itself. So one way I could use those functions is to create some intermediate variables. And so this is a let expression. I'm going to set the variable d to the result of this, and notice the in keyword at the end. So what's happening here is that this variable is only defined within the expression that follows in. So that's this part, but I can have as many of those as I want. And so now s is defined in the expression that follows this in. And so I'm squaring the value of d and then finally printing it out, and that's going to print out 16. Well, another way I could do this without the intermediate variables is what you're used to in other programming languages. I could call double on 2 and then pass that result to square and then pass that result to print int. And so I've got all these nested parentheses to enable that. But I could get rid of those parentheses if I use either one of the function application operators. And so if I use the double ampersand, then this applies from right to left. And so it's going to know to evaluate this first, and then take that result and evaluate this, and take that result and evaluate this. But a lot of people feel that it reads better if you go in the opposite direction. Really, what I want to do is take the number 2 and push it through a sequence of functions. And so here I take 2 and I feed it into double and I get 4. And then I feed that into square and I get 16. And then I feed that into print int and it prints it out. And one thing that's nice about this is that if you choose a font in your code editor that supports ligatures, it knows to combine certain characters, and these are 2 that it knows how to combine. And so what you'll see is a right pointing triangle. I think that's really cool. I love seeing that in my code instead of these separate characters. So let's look at a slightly longer example that shows using that function application operator. And there are also several other concepts that are being introduced here. So we already saw the open printf. I'm just trying to make the values it defines available so I don't have to prefix them. The next thing I'm doing is I'm defining a record type. So item is a record that has the fields description and price. And you see I specified their types. Description's a string, price is an int. And I'm going to represent my prices as a number of cents, so I don't have to worry about decimal places. Then I've got a tax rate, and then I want to describe a cart full of those items. So this is a list. And I know it's a list because the syntax for list is to use square brackets and to separate all of its elements with a semicolon like that. And then I have some literal records in here. I've got eggs and milk and bread, so it's a list of records. So one way that I could compute the cost of this cart is to use all this code that you see right here. So I could use fold left, which is like reduce in JavaScript, and I'm passing it an anonymous function. Note the use of this keyword fun. That's how I define an anonymous function. And it takes two arguments, an accumulator and an item. And I'm going to iterate through a list. This is the list right here, cart. And I start with a value of 0 in the accumulator. And so it's just iterating through them and adding to the accumulator the price of that item. And now I have that total, but remember I said the prices are in cents. So I need to convert that to a floating point number because I can't multiply an int by a float. It doesn't automatically do those kind of type coercions. So there are many functions like this one, float of int, for doing specific conversions. And so I'm converting subtotal to a float, and now I can divide by 100. Notice the periods here and here to make sure I'm using floating point operations. So I get that result, and again, notice the keyword in here and in here. What that's doing is making these variables subtotal and float subtotal available in the expression that follows. Now I can compute the tax by multiplying by the tax rate, and then I can compute the grand total. It's the float subtotal plus the tax, and now I can print it out. So this code's fine, but we could do the same thing using that function application operator. And so here, I think this is a bit easier to read. I'm telling it, take the cart and pipe it through this. And so this ends up being passed as the last argument to fold left. This part of the code looks the same. And I would take that result and I want to convert it to a float. And then take that result and I want to divide by 100, or in this case, multiply by 0.01. Then the last thing I want to do is add on the tax. And so if I multiply by 1 plus the tax rate, that'll give me that same result. Yeah, so I'm really liking this function application operator. There are a lot of things in OCaml that count as expressions. There's literal values like 3 or the string hello. A variable on its own is an expression. Let expressions that we've looked at that begin with let and they end with in. So you're setting some variable and then that will be available in the expression that follows in. There's keyword expressions like if and a for loop. Function calls like doubling the value of some variable. And then I can have a sequence of these that are separated by semicolons. But there's an important thing to take into account here, and that is that if I have a sequence of expressions separated by semicolons, only the last one can have a value. All the ones before, they have to be unit, because if they weren't, I'd be throwing that away, and I'm not allowed to just throw stuff away unless I explicitly tell it. So if I use the ignore function, I can say, yes, I'm calling this function add dog that's going to have some side effect, but it also returns to me a dog record, but I don't want it. And so I call ignore on that. And of course, I could use that function application operator to move ignore to the end if I wanted. It would be the same thing. And then I can do something. And so notice this semicolon and this semicolon. So the first two, they can't have a non-unit value. And they don't because I used ignore. And then finally, this one could have a value if I wanted it to. All right, let's talk a bit about modules. So in OCaml, all of the .ml files that you define, they create a module. And what it does is it takes the name of the file and it uppercases the first letter, and that's the name of the module. And that's because in OCaml, all modules have to start with an uppercase letter. So what can I put inside one of these ML files? Well, I could have open statements like we saw earlier. I could have include statements. And this is a different way of pulling things in. I'm taking things, not text from a file and including it as text, but values defined in another module and making them available here. I can have type aliases. It's a way of kind of defining custom types and giving them a name. I can have custom exceptions that I define. Then let definitions. This is really the main thing that you find in these files. You're either setting the value of a constant or you're defining a function and giving it a name. And then finally, I could have module definitions inside my module. It's a way of having nested modules. So often what you're doing with a module is describing a custom data type along with ways to create instances of it, and then operations that you perform on it. So there are many of these in the OCaml standard library that you see listed up here, like array and hash table and list and so on. And there are also modules in the standard library that don't define a data type. They're just a collection of functions that you can call. But interestingly, in a module that defines a data type, you don't typically define a class with methods. You can do that. It's just not the standard way of doing things in OCaml. What they prefer is that you describe a data type, how can I create instances of it, and then functions that I can call where I'm going to pass an instance to the function. And so it's not a method on an object. And so here's an example of that. Here I've created an array, a list of numbers. And what I want to do is I want to create a new list where all those numbers are doubled. And so the list module in the standard library provides a map function, and I can pass that another function. In this case, I'm using an anonymous function that's going to take a number and multiply it by 2, and then I give it the list. And so the point here is that the list module doesn't define a class for creating list. It defines a type that is a list and then gives me functions where I can pass instances to it and it'll operate on that. So if you want to define your own modules, one thing that you can choose to do is have an ML file and an MLI file. So the MLI file is for defining the interface to your module, and it's also a great way of specifying types. And so in this case, my MLI file is describing that I want to have this type, MLI is over here. I want to have this type point, and its type is float star float. Well, that's defining a tuple. It's a pair of values that are both floats. And so I'm going to treat the first one like an x coordinate and the second one like a y coordinate. And then I have this function distance that takes 2 points and returns me a float, the distance between them. And of course, as we saw earlier, if I pass it 1 point, it'll give me a new function that expects 1 more point. So down here for using this, I'm creating a point, and this is the syntax for defining a tuple. So I've got a point at 0, 0, another one at 3, 4, and then I want to ask for the distance between those points. Well, all of this code is going to be part of some library that I'm working on. And in my case, the name of the library is module demo. And then because the name of this file is math.mli and that one is math.ml, then the name of the module is math with a capital M. And now I can call distance and pass it 2 points. And that's going to be assigned to D. And then here I'm just asserting that it has to be 5. And if it isn't, that's going to throw an exception or raise an exception. So I've defined the interface for this, and then over here is my implementation. Unfortunately, I have to repeat this type definition for point in both. I'm not sure why there isn't a way to just put it in one place, but I've asked about that, and apparently I have to repeat it. Here I've got this function that can square a number, and I don't want this to be used outside the module. And you see that that function is not defined over here in my interface. And so it won't be exposed just because I didn't put it in both places. But my distance function is described in my interface. And so here's its implementation. So we saw here that I passed it 2 points. And this is a way of destructuring the points as I pass them in. This is the syntax for a tuple. And so it takes the x and y values out right in the parameter list. And now I can compute the dx and the dy values, and then I can call my private square function and then return the result of that. So modules give you a way of describing what you want to be in your public interface and then have some things that are private in the implementation. So OCaml supports some features of object-oriented programming, but as I said earlier, they're rarely used in OCaml code. So I'm not going to spend time talking about that. There are a lot of collection types that are supported by OCaml. Tuples that I mentioned are an immutable set of values that can have different types. They don't all have to be the same type. Unlike a list, where all the elements in a list have to have the same type. A list is also immutable, and it's an ordered list of things. It's actually implemented with a linked list, which makes it really efficient to create a new list from an existing one by putting the new element at the beginning of it. Association lists are an immutable list of tuple pairs. So you could think of each tuple as having a key and a value, and it's a list of those. So you might use this in the same places where you would use a hash table in other languages, but it would really only be appropriate if you've got a small number of these key value pairs. If it was a large number, you really should use a hash table so that the lookups will be more efficient. Arrays are different than these other collections we've seen in that they are immutable. So I can change the elements that are in an array, but I can't add to the array. Its length is not going to change, but I can change the value of elements that are inside it, and all the elements have to have the same type. We saw an example of records for the items that were in my cart. So that's an immutable collection of named fields. Actually, I need to correct this slide a bit. By default, all the fields are immutable, but as we're going to see coming up, I can mark certain fields and make them be mutable. Then other kinds of collections that have their own module in the standard library. There's a set module, there's maps, there's hash tables. The difference between map and hash table is that maps are immutable and hash tables are mutable. Many of these collection types have a literal syntax, all the ones that you see here. So tuples, it's just values in parentheses separated by commas. That's the only one of these where the literal syntax separates the elements by commas. All the rest use semicolons. So here's a list, here's an association list. Notice I've got tuples inside my list separated by semicolons. And then an array, you have to add vertical bars inside the square brackets. It's a little odd looking. So I suppose it's the case that arrays are not used nearly as often in lists as lists in OCaml, and so that syntax maybe doesn't come up quite that often. And then we saw this syntax for defining records. I've got names of fields with values separated by semicolons. Pattern matching is really one of the most powerful features of OCaml, and as I said earlier, it's kind of like the combination of destructuring and switch statements in JavaScript. So one of the rules about pattern matching is that they must be exhaustive. So if I want to list all the things I'm matching against, it must be the case that every value I could possibly evaluate has to match one of those things. And we'll see on the next slide what the options are for making sure that that happens. So in this example, I'm defining a type, a record type that is a player. My players have a name and a number and a Boolean to tell me if they're active in their sport right now. And then I'm creating a specific player, Wayne Gretzky, number 99, active is false. And notice that I have the same name for my type as I do for player, and that's not an issue. Also notice that I never said that this had the type player. It just saw what field names I was using, and it looked at, well, what do I know about? Oh, I know there's this type player that has those same fields. I guess that's a player type. So it figures that out automatically. So down here, I take my player and I'm using this pattern matching to destructure all of those fields. And so now I have the variables name, number, and active set to the values that came from that player record. And then I can check whether the player is active. And if they are, I'll print out Wayne Gretzky wears number 99. And if active is false, I'll say Wayne Gretzky is no longer active. Well, I could do the same thing with a match statement instead of an if statement. This is particularly useful when you're matching against more than two things, but you can have just two matches. And so this one says, I want to match player against a record that has a name and an active field. But I have a when here, and so I'm saying I only want to evaluate this printf if active was true. Well, active isn't true for mine, and so I go on to the next one, and I destructure out the name and the number and print out Wayne Gretzky wears 99. I actually said that backwards. This one is only if they are not active, and so I would print out Wayne Gretzky is no longer active. So notice that this does match every possible value of that kind of a record, because if this wasn't true, well, there's nothing stopping me from matching this. I know all players are going to have at least those two fields. But as I said, there are many things that you can match on. You can match on a constant value like 7 or the string summer. You can match on a range of characters. A variant type constructor. We haven't seen those yet. I'm going to be talking about that in just a bit. Matching against tuples. So if I match against this tuple, I'm saying, I don't care what the first value in the tuple is, but the second one must be the string summer. And then I want to destructure out the value of the third one because I'm going to use the value of temperature in the expression that's on the right. I can match against an empty list, or this one says it has to be a list where the first one is summer, and then I want to get the value of the second one, and I'm going to use that. And another way I could write this is with this cons operator. So this says I'm matching against a list, and I want you to give me the first element, the second element, and then a list of the rest of them. And so I have access to all three of those things in my match expression. Can match against an empty array, or here I have an array where the first element must be the string summer, and then I want to get the value of the second element. Can match against a record. We saw that in the previous slide. I can match against multiple things, just separating them by vertical bars, and if I match any one of those, I'm going to evaluate the expression on the right. And I can match against just a variable, and that says, I'll match anything, just give me the value, and then I'm going to use it. And we saw an example of the when keyword, so I can be more explicit, match against any value n, as long as that value is between 7 and 9. And finally, I can use an underscore to say I'll match against anything else. And so that helps me to make my match exhaustive, because I can just say, well, I matched against some things already. If there's anything else, use the last expression. Recursion is a powerful feature of OCaml. And so here's an example of how you could use that to calculate the sum of a list of numbers. So if I want to write a function that's recursive, I have to include the rec keyword after let. I have to tell it that I'm defining a recursive function. So the name of my function is listSum. I'm passing it a list, and then I match against these possibilities. And notice how this is exhaustive, because either my list is empty or it has a head and a tail, where the tail might be empty. So if I have an empty list, the sum of all those values is just 0. But if I have a head and a tail, then I want to add the head to the sum of the tail. And so it's going to call this recursively, and I'll end up with the sum of all of those. Well, this pattern is very common, where I pass it some value that I want to match against. In this case, the list, I'm matching against the list. That they came up with a shorthand for this, which is to use the function keyword. And these lines are the same, but notice what is left out here. I no longer have to say anything about the parameter, and I don't need the match L with. I just say function. And so this is equivalent to that, just written a bit shorter. So with those functions in hand, either one of those, I have my list of numbers, and then I can calculate their sum and print it out. But there's even a shorter way I could do this using a function from the list module. I could use fold left, which, as I said, is like reduce in some other languages. And I could just say the operation I want to perform is plus, and I want to begin with a 0 in my accumulator, and then just iterate through those and perform this operation repeatedly on the accumulator and the next number in the list. OCaml supports algebraic data types, and it's one of the things about these functional programming languages is that you get to use lots of fancy terminology And it sounds really impressive. So what are algebraic data types? Well, really they break down into two categories. There are product types and sum types. And what's a product type? Well, you could think of that as it's this and this and this. It's a bunch of things together, whereas the sum types are this or this or this. And so what's a concrete example of this? Well, a tuple is a product type because I have a bunch of values. I have this value and this value and this value. And a record is a product type. I have this field and this field and this field. Over on the sum case, we have variant types. And I said earlier, these are like an enum that can have associated data with each case. And so it's either this case or this case. It's one of them. So if I used a tuple to describe a point in Cartesian coordinates, I could think of the first one as the x-coordinate. It's a float value. And the second one, the y-coordinate, is a float value. Well, this is the Cartesian product of all of those. You could think of this as being a combination of every possible value for x combined with every possible value for y. And that's why it's called a product type. Over here on the variance, if I have elements in a list, what are the possibilities? My list could be empty, or it could have a head and a tail. There's only two possibilities, but it's got to be one or the other. Likewise, for trees, a tree is empty, or it's got a node in the tree that can have left and right children. There's a limited number of possibilities, and so that's a sum type. So as I said, variant types are like enums in other languages that can have associated data. And the terminology here is that these things are called constructors, or sometimes they're referred to as tags. And so my color type is either red or green or blue. And so I can assign one of those constructors to a variable, and then I can pattern match against it and say, well, if the value is red, I want to print that. If it's green, print that. If it's blue, print that. So this is an example of a variant type where the constructors do not have associated data. But here's an example of a variant type where I do have associated data. I have these constructors circle and rectangle for two kinds of shapes. And how do I want to describe a circle? Well, I'll make it be a record that has two things. It has a center and it has a radius. And the center is just a point, which is this tuple that holds x and y coordinates. A rectangle also has a point to denote its lower left corner, and then I have its width and its height. So I can now create a variable that holds a shape, and it's either a circle or a rectangle. And then I can start writing functions that operate on shapes. So I have this function area where I pass it a shape, and it can use pattern matching to determine which kind it is. If it's a circle, then I can destructure the radius, and I don't care about the center. I don't need that for computing its area. And then I can do this bit of math here and compute its area. For a rectangle, I need the width and the height, but I don't care about the lower left, and then I can compute that. Similarly, I can compute the center of a shape. If it's a circle, well, I've already got it. It's just sitting in the center field. And so I pull it out. Here I put it in the variable c, and then I just return c. If it's a rectangle, I need the lower left. And notice I'm destructuring the tuple right here and getting the x and the y values. And then I need the width and the height. I put them in shorter variables, and then I compute its center. So down here, I'm ready to create a circle, create a rectangle, and then I can call the area function, passing it either the circle or the rectangle. Similarly, I can compute the center of those two things. Okay, so that's a good example, I think, of defining a variant type where the constructors have some data that goes along with it. There are two built-in variant types that are commonly used, and one of them is option. The option variant has two constructors, none and sum of tick A. That is a red alpha. And so what this means is that it can be any type that it holds on to. So this is great for representing things that are optional. Either there is no value, and I call it none, or there is a value, and the value that it is what is held by the sum constructor. So It's common in OCaml that if you write a function that returns one of these option values, that the name of it ends in _OPT. And an example of that in the standard library is that the list module has a find opt function. So you're looking for something in the list and you might not find it. And if you don't, it's going to return none. But if you do find it, it's going to return some holding the value that it found. And so here I'm passing it an anonymous function. And let's assume that students is a list of records describing students. And one of their fields is their name, and another one is their score, perhaps on a recent test. And so here I'm trying to find a student whose score is at least 90. And this is just going to find the first one. There's another function I could call if I want all the students that match, but this is just giving me the first one. And so again, the value I get out of this is an option. I'll either get none or I'll get some that holds that student that matched. Result is kind of similar to option. This is used when something might not work. And so the variant, the constructors are okay or error. So if it worked, I get back an okay holding the result. If it didn't work, I get an error constructor holding a description of that error. Okay, so there are some functions that return an error instead of an option. And this is an alternative to raising exceptions. Talk about exceptions. There's a built-in type called EXN, which is kind of special because it's a variant, but it's an extensible one that you can add more constructors to it. So there's about 30 built-in exceptions, and then you can define more using the exception keyword. If you want to raise an exception because something went wrong in a function, you call raise and you give it the exception. If it's an exception that has data that goes along with it to describe it, then you can pass the data in that way. Then if I'm going to call this function and I want to catch exceptions that are raised, I use this try syntax. There's some expression that goes here, and then the with keyword. And then this looks like what comes after a match, a matching against different kinds of exceptions. In this case, if there were data that went with it, I can destructure that out and then use that in the expression that follows. So here's a concrete example of using this. Lots of functions that can raise an exception, their name ends in _exc. Unfortunately, not all of them. And this is an example. The list find function will raise a not found exception if it doesn't find something that matches the predicate function there. So here I'm looking through the students again, trying to find one that has a score of at least 90, and I'm going to get back either that student, in which case I can print out their name, or if it couldn't find one, it would have raised that not found exception. And so I'm doing all of this inside a try, and then I'm going to catch the not found exception and do something with that. Raising exceptions is kind of a common thing, and so there are some convenience functions that make that easier. So fail with, I pass it a string, and that will raise a failure exception that holds that string in it. And invalid arg is similar. I give it a string, and it raises that kind of exception holding the string that I gave it. So this means I don't have to define a custom exception type. I can just use those as long as I'm okay with the failure and invalid argument exceptions that are built in. I mentioned that OCaml has limited ways that you can do mutation, and so I want to talk about a few of those. The first is to use refs. So a ref is held by some variable, and you can't change that. It's always going to refer to that ref. But inside the ref, it holds a value that you can change. Interestingly, these are implemented by records that have a mutable field that is called content. And you can access that directly if you want to, but there's some syntactic sugar to make this easier. So we saw that exclamation point operator when I was showing the list of all the operators. That returns to you the value of the content field. So writing exclamation R when R is a ref is just shorthand for saying r.contents. Likewise, if I want to change the value, well, I use this : operator, and I can change my ref to that value. Again, it's changing the content inside it. But I also could say r.contents and then the arrow v, because that's a mutable field in my record, and that's the syntax for changing the value of a record field. There are also built-in functions incr and decr if your ref is holding an integer value and you want to increment it or decrement it. And so in this example here, I'm creating a ref that begins by holding 0. That's what's in score. And then I want to bump up the value by 1. Well, one way I could do it is by pulling out the current value, which is 0, adding 1, and then putting that back into my ref. But an easier way would just to be call incr on that, and I can call decr on that, and then finally print it out. So in this case, it's going to print out 1 because I went from 0 to 1, 1 to 2, and then from 2 back to 1. I mentioned earlier that you can mutate all array elements. So if you want to get a value out of an array, this is the syntax for it. Notice that it's not an array name followed by square brackets like in most languages. You have to have the dot and then put the index inside parentheses. And then if you want to change it, you use this arrow operator. And so here I've got an array of numbers. Notice the syntax with the square brackets and the vertical bars. And if I want to change the value at index 2, which is the 3, then this is the syntax for doing that. And I've just changed the 3 to a 4. I mentioned that you can mark fields in a record as being mutable, and here's how you do it. You just use the keyword mutable in front of the name of that field. And so now I create a record, and if I want to change the score, I can because it's mutable. And so I can just set the score field to the result of this. The successor function just takes a value, you pass it, and gives you 1 more than that. Okay, and finally, the hash table collection is what you use for creating a mutable hash map. So I create one just by calling create, and this 10 here is me giving it an estimate of how many things I think I'm going to put in it. It can allocate space more efficiently, and it won't have to rehash as often. But no matter what you put there, it's always going to work. It just might not be as efficient if you don't give it a good estimate. Then I want to add on to that. And remember this convention in OCaml that modules give you functions that operate on a data type. And so the hash table is in dogs. I'm passing that to the add function. And then this is a key and this is a value. And so that's now in my hash table. If I want to change the value associated with that key, I use the replace function, and I've changed Comet to be a greyhound. And then finally, I'm removing that key out of the hash table. I mentioned the standard library several times. Some companies have looked at the standard library and decided that they have better ideas on how the standard library should work. And Jane Street is, I suppose, the most popular of companies that have done this. And so they have an alternative to the standard library. There are 2 of them, actually. There's one called Base and one that's called Core. And so you can choose to use those. You install them with OPAM. And then in your code, if you say open base or open core at the top of your file, now you're using their standard library instead of the one that comes with OCaml. This is a little bit controversial because it kind of splits the community into these people that are using the standard library or people that are using the Jane Street version. So I'm getting close on time, and I want to make sure I cover some things here at the end. So I've talked about the OPAM package manager, and this slide tells you how to install packages using that, and then goes over this concept of switches. In other programming languages, you might be familiar with this idea that each project might want to use a different version of a compiler and a different version of libraries, and how do you keep these all separate? So switches are the way that you do this in OCaml, so that you could have global switches, which are sets of libraries in a version of OCaml that are used by a bunch of other projects, or I can have local switches that are specific to one project, and then as soon as I switch into the directory of that project, it automatically activates that switch, so I'm using the versions that are appropriate for that project. I mentioned Dune. As soon as you're combining multiple source files into a project and you depend on many other libraries, you really ought to switch over to using Dune. And so this slide shows how to create a project that will use Dune. And then once you've done that, how do you build your project? How do you run your unit tests? and how do you execute it. Each project can have more than one executable target, and so that, you can specify which one you want to run. Dune has a specific file structure, and so this slide talks about how you should be organizing the files. And if you use that dune init command, it sets this up for you. Every directory in your Dune project has a file that is just called Dune, and that identifies what kind of thing is described by this directory. Are you describing an executable, or is this a library that other directories use, or is it a set of unit tests? And it can also describe pre-processing steps that you want to be run on your code, and that's kind of like a macro system where it can generate some code for you. In fact, that's what this slide covers. This is used for generating functions that can operate on instances of some type. So a classic example of this is that if I define a record type that is my player type that you saw earlier, if I want to be able to convert one of those records to a string representation, well, I could write code that does that, or I could just use this syntax here, this deriving show. And this is an example of using a preprocessor extension to look at my type and generate a function for me that can do that. And now I have this show int list function that I can call whenever I want to convert that kind of a thing, in this case an int list, to a string. So it's a powerful way of doing some code generation, but it also can allow supporting new syntax that isn't a standard part of OCaml. And it can also add more static analysis to do type checking that I couldn't do otherwise. There's a list of resources if you want to check more out about OCaml. There's the OCaml homepage, and I got to say that the OCaml Discord server is wonderful. Every programming community wants to say that the people in it are very nice and very helpful. I don't think I've encountered a nicer community than that one. People seem so eager to answer my questions, and so that's what's helped me to learn about this quickly. My blog page on OCaml goes into way more detail than I was able to cover here, and I have a GitHub repository with a bunch of example code. Another thing I highly recommend is this book that is used in a course at Cornell University. And the professor that wrote the book and teaches the course created a set of YouTube videos that he used during COVID when nobody could come to his class, and he made them all available for free. I think there are around 200 videos, and they're all like around 5 or 6 minutes long. I'm almost through with it, but it's taken me a long time to get through them, but they're very well done. And then this is a book I'm reading right now, Real World OCaml. It kind of slants towards using the Jane Street libraries, but also a very good resource. So to wrap this up, I think OCaml is a very interesting functional programming language. It's got a lot of the features that you'll find in Haskell, but more pragmatic in terms of being able to mutate things and have other kinds of side effects. The type inference just blows me away, that I don't have to specify types, yet I still get really strong and static typing without having to tell it. The compiler just figures it out. There's some advanced features of OCaml that add some complexity, like functors and GADTs that I didn't talk about and I don't fully understand yet myself. But I think the biggest thing standing in the way of OCaml being adopted is that the libraries are not very well documented for some reason. And there's just not a lot of example code out there showing you how to use the libraries. It's kind of a surprising thing to me. I've authored some open source libraries myself, and I always feel like if I'm going to take the time to create this, I want people to use it. And so I really want the README on that to be detailed, or else nobody's going to use my library that I spent all this time on. For some reason, that hasn't happened in the OCaml world. However, some of the people that are really involved in OCaml are working on expanding the Learn section on the homepage and adding a bunch of cookbook style things here to supply just what I said is missing. And so hopefully that will improve soon. So as I said when I advertised this talk, it may be the case that you never end up using OCaml, and that's fine. But hopefully you've seen some ideas here that inform you about why people like a language like OCaml and why maybe you should want some of these features to find their way into programming languages that you currently use. So that's it. Thanks a lot for attending. And yeah, you can let me know if you've got some questions.